Hello, honors pre-calculus students, Mr. Gazzetto. Today's learning target is to talk about distinguishable permutations. So we're going to look at several examples today. The first problem, we want to list out all the different arrangements of the letters in the word keep. So I'd like you to pause the screen and try that. So let's see if you've got them all. So it could be K-E-E-P. It could be K-E, and we could switch the last two letters. Maybe it was K-P-E-E. It could be E-K, E-P, E-K-P-E, so I could switch the last two letters. It could be E-P, K-E, E-P, E-K, E-E, P-K, E-E, KP. So if you notice, I'm trying to use a pattern. So the first three I did start with the letter K. Then the next problems all started with the letter E. So what am I missing? Starting with a P. So it could be P-E-E-K. I could switch the last two letters. And then it could be P-K-E-E. So there are 12 distinguishable permutations of the letters in keep. And just for clarity, if you have K-E-E-P, if I put subscripts on these two E's, you can't really tell the difference if I switch it. So if I were to write K-E-E-P, that's the same as K-E-E-P, but I actually switched the two E's. If I were to put subscripts, now you can tell. So originally, you may have thought, well, there are 4 letters. So if you were to draw 4 dashes, you might say 4 times 3 times 2 times 1, so 24. However, in this particular problem, the answer is 12. Let's take a look at the next problem. How many permutations of the letter in the word mommy are there? Again, pause the screen and write them out. There are a finite number. Let's see how you did. And when I wrote them all out, I found that there were 20 different ways to rearrange the letters in mommy. So like we did before with keep, if I have the letters in mommy, I might draw 5 dashes, 1, 2, 3, 4, 5, 5 choices, 4 choices, 3 choices, 2 choices, 1 choice, or 5 factorial, or 120. However, the answer here is only 20. So what's going on here? Why is the answer in mommy not 120, but 20? And why is the answer in keep not 24, but 12? Some of you may already realize, well, in the letters keep, there are 2 letters. So you might have said, well, 24 divided by 2 is 12. Then in mommy, you might have said, oh, 120, and you might think divide by 3. But if you divide by 3, you do not get 20. But if you divide it by 3 factorial, which is 6, so 120 over 6 is indeed 20. So why do you have to divide by 3 factorial? Again, if you were to put subscripts M1, M2, M3, there are 3 factorial or 6 ways to rearrange the letters M1, M2, M3. Likewise, technically over here in keep, it is 2 factorial, but 2 factorial is 2. So this is called distinguishable permutation because letters are repeated, and if you rearrange them, you cannot tell the difference. So let's look at the following problem number 3. So if you look at this problem, you got a medication, and you want to look at how many letters there are. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters. So you might start out with 12 factorial. But then if you look at this problem, there are 3 A's. So how many ways can you rearrange the 3 A's? 3 factorial. So I'm going to divide by 3 factorial. Then you might want to look at the T's. There's 1, 2, 3 T's. So I need to divide by another 3 factorial. There's only one O, there's only one R, one V, one S, one I, and one N. So technically you have to divide by 1 factorial, 1 factorial, 1 factorial, and so on, but we typically do not write them. So all the ways you can rearrange the letters in this medication would be 12 factorial divided by 3 factorial, 3 factorial. So doing that on your calculator, you will get 133,056,0,0. Let's take another example. Suppose you had my last name, Cusado. How many ways can you rearrange the letters in my last name? Well, there's 1, 2, 3, 4, 5, 6, 7 letters, so 7 factorial. Divide by, there's 2 A's, so I need a 2 factorial for the A's. And there are 2 Z's, so I need a 2 factorial for the Z's. Doing that on your calculator, you get 1,260. Let's move to the next problem. How many ways can you misspell the word bookkeeper? So I would like you to pause the screen, try this problem, and see what you end up getting. So let's see how you did. So when you look at this word bookkeeper, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. There are 2 O's, so I need a 2 factorial. There are 2 K's, I need another 2 factorial. And then there are 3 E's, so I need that 3 factorial. So you'll get 151,200. But note it says misspell. So there's one correct spelling of bookkeeper, meaning bookkeeper. So the final answer here is equal to 151,199 because you need to subtract 1 for the one way to spell it correctly. So the learning target today was to talk about distinguishable permutations. Here's what you typically see in textbooks. So if there are n objects, then the formula would be n factorial divided by, and let's suppose there's n1, something is repeated, so then it'd be n1 factorial. Let me write that as a subscript, n1 factorial, and then there was, suppose n2, then it'd be n2 factorial, n3 factorial, and so on, all the way down to nk factorial. Now the reason they go all the way down to nk is sometimes a lot of these would be like 1 factorial, 1 factorial, 1 factorial. So in the bookkeeper problem, we didn't divide by the 1 factorial for the b, for instance. Let's look at a different type of problem. So in problem number 4, how many ways can I go from home to school only going west and north? So I'm starting at home and I want to go to school. How many ways can I accomplish that? Well, you might imagine, well, I could go this way in yellow. I could go this way in blue. I could go this way in green, and so on. So how many ways can I travel from home to school only going west and north? So if we look at this particular problem, if you want to pause the screen before I talk about the solution, please do so. So if I look at the screen, going from home to school, I have to go west 5 times. 1, 2, 3, 4, 5. I also have to go north 4 blocks, or 4 times. So this is a distinguishable permutation. If you count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. And you want to rearrange those letters. It doesn't matter if you go do all the wests, like for instance in yellow, and then you go north. You could have went north and then all the wests. So how many ways can you rearrange these letters? 9 factorial over 5 factorial, 4 factorial. So when you type that into your calculator, 9 factorial divided by 4 factorial, 5 factorial, you get 126 different ways. I also want to show you another way a student did this last year. So one of your classmates said, well, if I start here at home, there's one way to get to that spot. Then this green dot, there are 2 ways to get to that spot. I can go north-west or west-north, so they put the 2 there. In order to get to these red dots, there's only one way, directly north or directly west. In order to get to this gray dot, they figured out that there were 3 ways to get to the gray dot. So you can try that on your own, but they figured out there were 3 ways. Likewise, this gray dot, they figured out there were 3 ways. To get to this red dot, there was 1 way. To get to this red dot, there was 1 way. Then they said, all right, well, how do I get to this blue dot? And they traced out all the different possibilities, and they figured out there were 4 ways. They then tried to figure out the second blue dot I just wrote, and they figured out there were 6 ways. And then this blue dot, they figured there were 4 ways. Then they said there was 1 way there and 1 way there. Then they said, well, this looks like a pattern. So they turned the picture upside down and saw it looked like the following: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And some of you may have studied this in the past. This is called Pascal's triangle. So it's a very interesting relationship here. So the student kind of continued this pattern. They said there was 1 way there, and then they figured this was 5, this was 10, that was 10, and that was 5. So they wrote 1, 5, 10, 10, 5, 1. And at this point, you may be realizing, how do you get this 4? You add 1 and 3, the 2 numbers kind of above it. How do you get this 10? You add the 2 numbers above it, the 6 and the 4. So then your classmate kind of continued this pattern and said this was 6, 15, 20, 15. This number, 21, 35, and 35. Here, when you add those up, you get 66, I think. No, 56. And same, this problem here, that blue dot is 70. So then to get the final answer there, they did 56 plus 70, 126. And if I go back to the distinguishable permutation way, you get the same answer. So I wanted to show you that there were 2 different ways your classmates did that. Let's take a look at our final example. So how many ways can I go from home to school again, but I need to stop at this green dot to pick up Mrs. Cazzato? So I consider this to kind of be 2 different problems. I need to go from home to the green dot, and I'm only going to travel the same way, west and north. So from home to the green dot, I have to go west 3 blocks and north twice. So that's to go from home to pick up Mrs. Cazzato. Then, to go there, from picking up Mrs. Cazzato to home, I have to go west twice and north twice. So this is 2 distinguishable permutations. So for the red, it would be 5 factorial over 3 factorial, 2 factorial. For the blue, it'd be 4 factorial over 2 factorial, 2 factorial. Doing the math, this first number is 10. And doing the math on the second number, you get 6. So now the question becomes, how do you figure out the final answer? Well, you need to do both. Go from home to pick up Mrs. Xato and then Mrs. Xato to school. So this is like the fundamental counting principle. There are 10 ways to do the first event, 6 ways to do the second event. So the final answer here is 60. So the learning target today was to talk about distinguishable permutations. If you really wanted to, you could do problem number 5 using Pascal's triangle, but I personally wouldn't. Hope you found this video helpful.